So on a lighter note, it is Monday and the start of a fresh week, and we're going to learn cool things. And you don't want to be in a hurry when you say bit shift, because you could end up saying. Anyway, let's go down to section E and F, and then we'll talk about hexadecimal. We want to spend some time reviewing what the hexadecimal number system is, and we want you to be capable of performing a manual conversion. Now, one of the things I'm going to share with you is that working in binary alone and decimal, you grew up with decimal number system, and we said that the binary number system is different and you have to unlearn some things. But if you also learn the hexadecimal system, there's a nice synergy that is created between the base 2 binary number system, the base 16 binary number system, and the decimal number system. Knowing all three allows you to convert between formats with ease. Knowing only binary and only decimal is tough. It's actually harder. So it's kind of like knowing a Romance language where you know some Espanol and French, Spanish, Italian, Portuguese, and one other language, I think, Romanian, and I could be wrong about that, but Latin, the language of Rome, became sort of like the basis for many of the words that are used in French and Spanish and so on. If you know Latin, or you know another foreign language, if you know another Romance language, it's much easier to take up a conversation and then be trilingual than it is to just do English and French or English and Spanish. So I want to challenge you to spend some quality time in hexadecimal, even though it seems like it's kind of a footnote here in this particular module. It's going to become much more important a little later on. Any questions about what I've shared about the powerful synergy of hexadecimal and binary?
So it's going to show up in later modules throughout the school year?
Yes, it is.
Okay.
So I wanted to finish this notion about bit shift, and then I want to jump back, and then I want to go back into bit shift later on, because if you do more than one place, all we're doing is finishing what we introduced. So if we shift one place to the left, if we take this number and we slide this string of numbers, 1101, and we move it so that the 1 starts here, we still have 1101, but this nibble and this nibble, remember a nibble is part of a byte, this becomes 0011, and this becomes 0100, right? So there's a second 0 here that's formed when you slide 1 to the left. These zeros, these extra zeros, are called trailing zeros. And you need to remember to add the extra 0 at the end, or the shift doesn't work. So as you slide this quantity over to the left here, starting here, you're going to have nothing there. This is going to get sucked over to this place. And then you're going to have an empty value in the ones column. And you have to put a 0 there. So the trailing zeros are very important. Don't forget the trailing zeros. Now, let's talk about what happens if you shift to the right. If I took this value, 1101, and I slid it to the right, my ones place would now have the 1. My twos place would now have the 0. My fours place would now have the 1. So, and I would lose this 1 right here. And as I slid to the right, I'd end up picking up a 0 on the extreme left boundary. Those are leading zeros. Okay, trailing zeros are off the right side. Those are gained when you're sliding left. Leading zeros are added when you're sliding to the right. But here's the catch, and this is one thing that you have to know. If I slide one place to the right, my 1 is on the rightmost boundary of this binary value. Because I have a non-zero value in the extreme, the least, it's called the, so these are considered to be more valuable or larger in quantity than those. Just like 3,000 is, the 3 in 3,000 is a more significant 3 than a $0.003. That's a less significant 3. In decimal numbers, if I have a 3,000, that's a more significant 3 than if I have a $0.003. Which one would you rather have? Well, which one's less significant and more significant? That's just common sense, right? The same is true of binary number systems. So what are we saying? The number values on the extreme right end are considered to be the least significant because it represents the 1's place, the 2's places, and the 4's place. So those are smaller values. The numbers over here formed when 1's are over here. The further you go to the left, they're more and greater significant. If you have a 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, that 1 represents billions in decimal value, okay? So it's much more significant when you park a 1 way on the end. And this is just intuitive. We do this without even thinking about it in the decimal system. The point I'm trying to make is that when you slide to the right, there is a catch. When you slide to the right, if you have a non-zero number and you slide to the right, and now you have 0, 0, 0, 0, 1, 1, 0, 1. Okay? As we take these 4 binary values and slide them one place to the right. I pick up an extra 0 here, and all 4 of these values are over there. I cannot slide to the right anymore because I have a non-zero value on the rightmost boundary of the number range. When I try to slide to the right, the 1 drops off the planet, it evaporates, and I lose part of my number value because I'm picking up extra numbers here, but I'm slowly losing the values of those trues or 1s for their placements as we slide off the right end. So you can keep sliding to the left. You're unrestricted in sliding to the left, but if you slide to the right and you get to the place where the rightmost 1 is in the last place, that's as far as you can take it. Now, I want to get back to this. If I slide to the left, I double the number. If I slide to the right, I cut it in half. If I slide it to the right, I take the original number and I cut it in half. Now, let's prove to you I know what I'm talking about. Can everybody see my calculator?
Yes.
Okay.
Yes.
Yes.
So I'm going to click on the binary option, and I'm going to type in this number. And then we're going to, and by the way, who knows what the decimal equivalent of this number is? Can anyone tell me? The 1's place has a 0, so I don't have any 1s. The 2's place, I have a 1, so I have a 2.
That's 6.
The 4 is empty. The 8 is there, so 2 and 8 is 10. This place is the 16's place. Now here's another thing. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4th is 16. That's another way to keep track of the value of each of these places. You just have to remember that if you're using in base 10, in base 2, if you're using exponents to explain this, the first column is 2 to the 0 power. Anything to the 0 power is always 1. So for any number system, the first place in the columns of numbers for any number system, it's always 1, right? And it could be 10, it could be octal. So base 8, if we were dealing with the octal number system, and some of you are saying, oh no, I don't want to hear about this. Well, just bear with me for a second. What's 8 to the 0 power? 1. What's the number pi to the 0 power? 1. What's the 100,600,523,000 to the 0 power? 1. So every number system pretty much has whatever number factor to the 0 power, it's the ones column. But then the very next column is the same as the base number. So in a base 8 number system, this would be the ones column, this would be the eights column. In binary, it's real simple. 1, 2, 4, 8, it doubles. You want to memorize those numbers all the way out to 512. And that should be something you've already seen in your study guide. Back to our calculator. I'm going to type in 0001. And it's not going to see, it keeps the leading zeros when I type them. Everybody see that? It's not showing it here, but it's showing it there. I'm going to type the rest of this number, 1010. Okay. What's the decimal value here?
26.
26. So if I take 2, 8, and 16, what does that make? 26, right? Now, I'm going to slide this one place to the left. So now I'm going to enter, everybody remember 26. This is 26. Everybody, 26. Repite usted, por favor. 26.
26.
26, right? Right, 26. So I have 26. Now I'm going to slide it one to the left. I want to prove to you that this bit shift actually works. So I'm going to take this value now and plug it into the calculator. I'm going to clear my calculator. And I'm going to put 00110100. If I look, that's what I've got right here. Twice, 26 twice is 52. What's the decimal equivalent of this? 52. Now what's 26 cut in half? 13 is correct. So let's see if I take these 4 binary values and I slide them one place to the right so that all 4 of those values are right here, and all I have left on the left nibble is 0000. So I'm going to clear this. Let's see if I get 13. 0000 1101. Right. Well, if I have nothing but zeros, it's not going to show here. So it's not going to show the nibble value of all 4 zeros. It's just going to show the 1. I have a decimal value of 13. So I took this and I slid it one place to the right. So if I slide to the left, I double. If I slide to the right, I cut it in half. Well, what happens if I slide it 2 places? Now it's quadrupled. 3 places. Now it's 8 times the value. 4 places. Now it's 16 times the value. What if I slide it to the right? 2 places. It's 1/4 the original value. 3 places to the right. It's 1/8 the original value. 4 places. It's 1/16 the original value. Does everybody see what's going on here?
Yes.
Yes.
Okay, it's pretty simple, but you just got to work with it a little bit, and it helps to have this programmer calculator out so you can see for yourself, okay? Now, why do you care? I'm not going to ask you to do calculations in your head. Not at first. But if you learn the binary equivalence of the hex values we're about to cover next, you will be able to do very complex calculations in your head, just like your computer does. And people are going to be amazed. And I'm not making that up. Okay. So now what we want to do is we want to blitz back to hexadecimal. And we want to talk about hexadecimal because we want people to understand hexadecimal is different. So in base 10, we use numbers 0 through 9. Because when we get to 10, we use the number 1 plus the number 0. We also add the number 0, and we have a 2-digit number. So when we reach 10, we're actually working with a 2-digit number. Everybody remembers this, right? From basic math? Yes?
Yeah.
The number system you grew up with, yeah. Now the weirdness, this is kind of weird, and again, it takes unlearning. In this course, I need you to see A, it's not a letter. Just like the plus sign is not the same as the binary function and. Even though plus and are verbally kind of stitched in the back of your brain, the plus symbol in binary operations represents which binary operator? Anyone? Does it represent? It doesn't represent and. What does it represent?
Or
Or is correct. And or is the binary operator that performs addition and actually performs multiplication. Now in here in the hexadecimal or base 16 number system, we run out of the Arabic numerals. So your decimal system is based on 10 Arabic numerals that, and we have the Arabian culture in the early stages after Rome fell and before we had the Dark Ages and, well, actually during part of the period of the Dark. If you look at world history, Arabs, the Arabs developed Arabic numerals, and what we use today has been adopted from them. So even though there's a lot of cool geometry that the Greeks gave us, right? The Romans had Roman numerals, and those were, they performed math with Roman numerals, and ooh, you talk about a weird mental wrinkle. We're not going there. Arabs came up with 0 through 9. So these are Arabic numerals. And actually, that is an amazing contribution. But the problem is that we just have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And when we get to 10, if we're dealing with a base 16 number system, we have to have some way of representing 10. And 11 would be B, 12 would be C, 13 would be D, 14 would be E, and 15 would be F. And you're like, whoa, Professor Ken, stop. You said F represents 15. Yeah, that's right. And we have a 16 number system, but F is 15. Where does the 16th value come from? I know that's a trick question. It's okay if you don't want to take a risk and answer. You have 1, 2, 3, 4. I'm going to take this non-printing character thing off. 5, 6, 7, 8, 9, A, B,
It would be
C,
A and F.
D, E, and F. If I count these, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 characters or 10 numbers. These are numbers. These letters are not letters of the alphabet. In this context, these numbers are the number A, which is kind of weird, but it is. This is 11, 12, 13, 14, 15. Now, we said that in the binary number system, you had the value 1, but you had one other value that made for 2 values. What was the other value in the binary number system?
Zero.
0 is correct. Give the lady a cigar. Thank you for jumping out there and taking a risk. Thank you. It is 0. Just like binary, we have 2 different values, on and off, 0 and 1. And those 2 numbers allow for a binary number system or base 2 number system. How do we make a base 16 number system possible? We have to have 16 values. And this is intuitive. Here we have 15 values, and oh, this is kind of weird. We're using letters instead of numbers, but where's the 16th value? It's this one. We have to have a 0 to keep, we have to have a 16th value. Again, let's not get into the, but 0 represents a non-value. It represents a non-quantity would be more accurate, right? So in terms of number theory, I'm going to leave that to the mathematicians and the, the faculty in the math department. When you take number theory, when you take, actually you take the logic course, right? You take discrete math, that's about logic. They'll get into some of this. The point is that you got to have a 0. If you don't have zeros, your number systems don't work because you have a number line and you have to hold your place in the number line. Just remember that 0 is every bit as important in the hexadecimal number system, and it's the first value. Now, I'm going to say this over and over again. We're going to try to trick you in the first assessment for Module 1, all the way through Module 6, and for your midterm and your final, I'm going to say, what's the first value of the base 2 number system, the base 10 number system, the base 16 number system? And what most people do is they go, the first value is 1. No. In hardware, you always designate the first device as the device 0. This is an industry practice. How do you number the first Ethernet card in a server, the first hard disk in a server, the first memory module in a server? It's memory module 0, hard disk 0, network interface 0, Wi-Fi card 0. Does everybody understand?
Yes. Yes.
The number used to designate all digital components worldwide, industry practice, ever since there's been an industry, 0. Display adapter. The first display adapter in any computer is given what number? Display adapter, everybody in unison?
0.
0.
0.
Yeah.
Do
Zero.
not let me trick you on the assessment. Don't say display adapter number 1, because it'll be wrong, and then you'll go, oh my gosh, I can't believe this. We did this on Monday, right? Yeah, oh, that was that Monday that we did this. Okay, all right. Any questions about that? Now, I'm hammering that. I'm going over that. Look at this. When you're dealing with numbering systems, what's the first exponent used to represent? It's always 0. And what is anything to the 0 power?
1.
Yep. So let's take a look at the hexadecimal number system. If I have a 3 number value in the hexadecimal number system, I have a 9 in the first place, I have a 9 in the second column, and I have a 2 in the third. I have an echo. So I'm going to use Alpha, Bravo, Charlie. I was in the Army. Everybody knows I was in the military, right? Oh, yeah. Yeah.
Hmm.
Yeah, I worked with nuclear weapons. Our motto was nuke them till they glow. And then the other person saluting you would say, and then shoot them at night. Pretty morbid, I know, but people who work with nuclear weapons have to train a little differently than everybody. Anyway, I'm getting back to this. I'm going to use the military language to talk through letters all the time. So Alpha, Bravo, Charlie, Delta, Echo, Foxtrot. If you want to use other names for these letters because you're part of law enforcement and you want to do something like David instead of Delta, that's cool. Okay, but that's what I'm going to do. And I just want you to understand where that's coming from. Now, let's look back here at our example. 2 Echo 9er, right? That's a 3-digit hexadecimal value. In the first column is the ones place. Why is it the ones? Because if we're dealing with hexadecimal, the base number is 16, hence base 16 number system. The base number is 16, but we're doing it to the 0 power. Why are we doing that? Because 0 is always the first value of a number system, even though it represents a non-quantity. Anything to the 0 power is 1. So this is the ones column. Now I have 9 listed here, which means I have to take 9 and multiply it by what? 1. So what's 9 times 1? 9.
9.
Yeah, yeah.
Uh,
So in the decimal system, what does this first column represent? 9. But let's take a look at this next one. Echo. Echo
14.
is 14. And in this case, when I'm dealing with 16 to the first power, my multiple in the second, notice my words, my multiple in the first column is 1. My multiple in the second column is 16. My multiple in the third column is 256. Okay, so I have 16 to the first power. I have a base number of 16, but this represents 14. So I have to take 14 and multiply it by 16 to get the value of the second column. So I have 9 already, yeah? So I'm gonna go ahead and I'm gonna switch back to a standard calculator and I'm gonna say 9 and I'm gonna add that to my memory. I'm gonna put it in my memory. Then I'm gonna have 14 times 16, because I'm in the second column, and I'm gonna have a number, it's 224. 224, okay? I'm gonna add that to my memory. That's gonna be 9 plus 224. I should have, when I hit recall, what's 9 plus 224? 233 maybe? Oh yeah, yay, okay, all right. All right, so I got 233. Well, let's look at the third column. Third column, I have the value of 2, but what's my base number in the third column? Well, this is 16 to the 0. This is 16 to the first power. This is 16 squared. What's 16 squared? 256. I have to take 256 and multiply it by what? 2. What's 256 times 2? 512. I'm going to add that to what's in memory already. Boom. Now I'm going to recall my memory, 745. Now here's what I want to do. I'm going to switch back to programmer mode. 745 in decimal. What does that equal to? Oh, look, hex. 2 echo 9. 2 echo 9. 2 echo 9. Okay. Now here's the fun part. And this is the most important thing we want to teach today. If you have a flavor or a taste for what the hexadecimal number system is, do I expect you to be able to convert between hex and decimal? You look at a number, it's like, okay, I have a hexadecimal value for the MAC address of my network card. So what is that in real terms as a decimal number? What am I talking about? Or let's say it's the memory address location that represents my network card. So I'm sorry, I'm going to go into device manager. I'm going to manage this. am I going to torture you by making you, where's our network card? Network adapters. Oh, there's my wireless card, okay? I'm gonna look at the properties. The address, the memory address location for the virtual wireless card, right? You see these hexadecimal values for the IRQ, right? Am I going to expect you to be able to convert to decimal from hex in your head? No, I'm not. But here's what I am going to expect you to do in your head. I want you to know the binary equivalence of each hexadecimal value from 0 to F, okay? What am I saying? Each hexadecimal value represents a nibble, 4 bits. Look at the calculator again. I have a 2. Oh, look, can everybody see this?
Yes.
Yes.
0, 0, 1, 0. Now, if I take just that nibble, I have a 1 in the second column, which represents 2. Here I have a 1, 1, 1, 0. I have an 8, a 4, and a 2. That's 14. That's the same as echo. See,
Oh,
14 is the end here. Look at this. 5, right? I have a 1. In the 2's column, it's empty. In the 4's column, it's empty. But in the 4's column, I have a 1. So what's 1 plus 4?
it's
5,
5.
right? Yeah. Yeah, that's the point. Oh, I'm sorry. I kind of messed up here. Remember I said we're working between hex and binary. So 9 is 1 plus 2, 4, 8. 8 plus 1 is 9. There's 9 here, and that's 1001. So this nibble is this hex value, this nibble is this hex value, and this nibble is that hex value. Now, I think somewhere we have a resource, or we have it in the study guide, where it shows you the binary equivalence of the, hang on just a second. We have the binary equivalence of each hex value in the number system. There's a table. And I think there are flashcards, right? So let me go here, 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 here. Flashcards. This should be in Blackboard. I want you to do this, right? So I kind of walked through this and I explained some things about how binary work. And what I'm doing is kind of walking through with each of the nibbles in hex, what they're worth. When you go all the way to the end, when you get to Foxtrot, another way to understand this, you have 4 values in binary, and then you have a hexadecimal value and you have a decimal value. So 0 to 15 in base 10 is 0 through F in hexadecimal. Okay, but what does it look like in binary? Well, this is 1. 0, 0, 0, 1 in binary is the same in hex as it is in decimal. That's all pretty easy. When you get down to 9, it's simple. But when you get down to 10, I want you to memorize that A is 1010. I want you to know this table. You have to memorize this table. Now, that seems like a lot, but it's going to be a worthy investment, because when you look at the hexadecimal number 7, but you know in your mind, okay, from 0 to 9, everything's the same in decimal and hexadecimal, right? It only changes when you get to 10, because we have single digit values in every number system, and the decimal system only runs from 0 to 9. It doesn't, it doesn't run to 10. Once you get to 10, 11, 12, now you're looking at a 2 decimal number, right? Hexadecimal runs from 0 to F. I want you to notice that all ones is F. If you add a 1, a 2, a 4, and an 8, you get 15. That's the decimal value here. If you add a 2, a 4, and an 8, you have a 14. If you add just a 4 and an 8, you have 12. Does everybody understand what I'm saying?
Yes.
If you add a 2,
Yes.
if you add a 2 and an 8, that's 10. But I also want you to know that that's the same as alpha in hex. So what do I mean? I want you to be able to convert a hexadecimal value into its binary equivalent. I want you to memorize these two columns right here. Let's keep it simple. I want you to memorize the binary equivalents of each hexadecimal value. And it's time to stop now. Are there any questions before we clear for the day? Going once. Going twice. Okay, we're going to stop sharing, stop recording.